In this video, we are going to be looking at the DES cipher, which stands for Digital Encryption System. We're first going to look at the Lucifer cipher, which is the original version of this cipher. Then we're going to give a simplified version of Lucifer, which is called the Digital Encryption System. And then we're going to look at some simplified versions of the Digital Encryption System, one of which we're going to actually learn and implement. We're going to give a sample encryption, and then we're going to show how our simplified version could be used recursively in a slightly less simple version that's a little more secure. Alright, so I just want to remind you first about the XOR cipher. That was a cipher that we use to encrypt bit strings. And it was pretty simple in that we actually transformed each bit into another bit. In other words, we encrypted each bit individually. Sort of like the substitution cipher. Lucifer is a little bit different. It's a cipher that takes a block of bits. In the case of Lucifer, that was 64 bits at a time, and transforms it into another block of bits that was also 64 bits. So instead of taking individual bits and transforming them into other bits, it took them in big groups. So in this case, the key bit is a bit string. The key goes through a process that converts it into actually many keys. The plain text message is, of course, converted into a bit string, because this is a more computer-oriented cipher. Then the plain text bits are split into 64-bit blocks, just so we can actually use the Lucifer cipher. And these are encrypted individually. So when we have a 64-bit block, here's the basic process that we go through. I'm not going to go through the details because they're horrendous. First, we're going to look at the first key that is generated from the original key. Remember, that original key we used to generate a whole bunch of other keys that we are going to use in our encryption process. We're going to split our plain text block into two 32-bit blocks. Remember, it was 64 bits at the beginning. Now we're going to split it into 32-bit blocks. One, the L0 is the left half, and the R0 is the right half. Using the first key and L0 and R0, we go through a really complicated process to create two new 32-bit blocks called L1 and R1. Then what we're going to do is put L1 and R1 through that same process as we did with L0 and R0 to get L1 and R1. To get another a pair of blocks, except this time, instead of using that first key that was generated by the original key, we're going to use the second one. Right? We're going to end up with an L2 and an R2. Again, each of those is 32 bits. And then we're just going to keep on going. We're going to go through this 16 times, or rather we're not, but if you used Lucifer you would. And that's going to end up with two 32-bit blocks, L16 and R16. And then we're going to encrypt that with the ciphertext R16, L16. We put the R16 first and then the L16 second. That gives us a 64-bit block. So this is a process that you go through by taking one 64-bit block and converting it into another 64-bit block. So this process, as you can see, is very complicated, and it's actually very secure. So secure that it scared the crap out of the NSA. And so the NSA said, you can't use this particular cipher. We got to simplify it for you a little bit. You're only allowed to use 56 bits for your keys. Ah, well. And when they did that, that was called the Digital Encryption System. So the Digital Encryption System is exactly the same as Lucifer, except the keys are restricted. Now, we're not going to learn the Digital Encryption System because it is horrendously complicated. However, someone named Edward Schaefer at Santa Clara University developed a simplified version that he called SDES. So that one used a 10-bit key. Right? We didn't go all the way up to 56 bits. This is just a 10-bit key. The block size of our plain text was 8 bits instead of 64, so that made it a little simpler. However, this is still too nasty for normal human beings. We are not going to learn this version. So we're going to learn an even more simplified version of SDES. I call it actually SSSDES. The reason I added two simplifications is we take a simplified version and make that even simpler. I will show you the SS, the other simplified version, at the end of this slide. But we're just going to go one round in this one. So what we're going to use, we're going to actually use an 8-bit key the block size of our plain text looks worse than the other one. Instead of 8 bits, we're going to do 12 bits, but it's actually going to be a little bit easier. We're going to just do one round encryption instead of the 16 that's used in Lucifer. And then at the end, I'll show you how to do multiple rounds if you wanted to do 16 rounds or however many rounds you wanted to do with a 9-bit key. All right, so first of all, our key is an 8-bit string, and our plain text is given in 12-bit blocks. Now, in real life, what we do is we'd encrypt this using, or encode this using ASCII, but then once we have that huge bit string, we're just going to break it into 12 bits when we encrypt it. But we're just going to encrypt 12-bit blocks one at a time. So what we're going to do is we're going to split the plain text of that block, of that 12-bit block, into a left half L0 and a right half R0. Each of those is going to have 6 bits. And then this is the general process that we're going to go through. So the L0 and the R0, those are up on top. Those are what we start with. And so we have this little flow diagram. Now let's start with the R0. So what we're going to do is we're going to take the R0 and we're going to put it through a little machine, well, call it a machine or a function that expands it to 8 bits. So R0 starts out at 6 bits. We're going to go through some process that expands it to 8 bits. We're going to scramble it, squish it back to 6 bits. And then what we're going to do, you see the XOR on the bottom, is we're going to do the exclusive OR operation between what comes out of that expansion and scrambling and the L0. So those are both going to be 6 bits. We do XOR, that's going to give us 6 bits again, and that is going to become our R1. So our R0 starts out at 6 bits, goes through this massive expansion, scrambling, and XOR stuff, comes out as R1. Now L1's has a little bit easier road to its creation. We just take R0 and that becomes L1. So not complicated at all. All right, and then the ciphertext that we're going to use is we're going to do R1, L1. So just like we did R16, L16 for Lucifer and Data Encryption System, we're going to do R1, L1 as our ciphertext. All right, so most of that was actually relatively easy to understand. The only part that I didn't explain in any detail at all was the expansion and scrambling. So I'm going to do that right now so you can see what it is. And when you see how complicated it is, you'll understand why I didn't include this in the diagram over there. All right, so let's start with expansion. Expansion is actually relatively straightforward. So remember, our R0 is going to have 6 bits, and we don't know what those 6 bits are. We know they're going to be zeros and ones, but we don't know which one's going to be a 0, which one's going to be a 1. So I'm just going to call those 6 bits R1, R2, R3, R4, R5, and R6. All right. So what we're going to do is we're going to scramble those around, or not scramble them around, but change the order of them a little bit. Right, so I'm going to take the 3rd and the 4th bit in the bit string, and I'm going to switch their order, and then I'm going to add another copy of that 3rd and 4th bit. So in the same reversed order. So I'm going to take that R3 and R4 and turn it into R4, R3, put in another R4, R3, and then keep the R1, R2, and the R5 and R6 the same. Okay, so all I've done is switch the order of them a little bit and added 2 spaces to the bits. So it used to be 6 bits, now it's 8 bits. That's why we call it expansion. Now, notice that now that that's 8 bits, that is now the same length as our key. Remember, our key is 8 bits. So what we're going to do is we're going to take that scrambled or that expanded R0. We're going to take the exclusive OR operation between that and our key, and that's going to give us another 8-bit string, right? So we took our R0, we made it into 8 bits, we did an exclusive R with the key, we end up with 8 bits again. All right, so now we're going to work our way back down to 6 bits. We're going to do it in kind of a funny way. The first thing we're going to do is we're going to take that 8-bit string and we're going to split it into 2 4-bit strings, a left-hand 4-bit string and a right-hand 4-bit string. And then what we're going to do is we're going to convert each of those into a 3-bit string from these, well, they call them S boxes for some reason. And here's the first S box, right? It's a box of a bunch of 3-digit binary numbers. And what we're going to do is take that, in S1, we're going to take that first 4-bit string and use it to choose one of those 3-bit strings in a way that I'll explain later, but we're going to choose one of those. Then we're going to take the second 4-bit string, use the S2 in a similar way to choose one of those 3-bit strings. And then we're going to take those 2 3-bit strings that we take from the S boxes and put those together to form a 6-bit string. Right? So let's see what we did. We took our R0, we expanded it to an 8-bit string, we did a bit of exclusive OR, we split that 8-bit string into 2 4-bit strings, smashed those into 3-bit strings, put those back together to make a 6-bit string. So we started off with a 6-bit string, ended up with a 6-bit string, and that is our expansion and scrambling. All right, and then after that, after we do the expansion and scrambling, the rest of it is actually pretty straightforward, right? We take those two 6-bit 6-bit strings, the L0 and what came out of our expansion and scrambling, and we do the exclusive OR operation on them, and then those become our R1, and then our L1 is our R0, and that's kind of the end of that process. So let's go ahead and do this on an actual key with an actual plain text block. So our key, I just chose for 8 digits of zeros and ones, 101101110. That's our key. Our plain text, we're just going to do one block of plain text. We're not going to take an actual message in English and do that. I'm just going to do one block of plain text, 12 bits, just to show you how this process goes. Doing long messages on this is actually pretty exhausting. So we're just going to do one plain text block. So when we split our plain text into our L0 and L1, remember our L0 is the first 6 bits of the plain text, which is 101101, and then R0 is the next 6 bits, that is 100101. All right, so what we're going to do, we're going to leave L0 alone for now. Remember, that's going to come in later to do an exclusive OR operation. First thing we're going to do is we're going to expand R0. And remember, expanding R0 means that we flip the 3rd and 4th ones, right? So the 3rd and 4th digits were 0, 1. Then we flip it to 1, 0. Then that 1, 0 gets repeated to another 1, 0, right? So we go, and the 1, 0 on the left and the 0, 1 on the right stay the same. So that gives us an 8-bit string for R0. Then we're going to do the exclusive OR of that 8-bit string with our key. Now remember, so there's our R0, 10101001. And then our key, remember, is 10110110. And then we're just going to do the exclusive OR. The 1, 1 gives us a 0, the 0, 0 gives us a 0, 1, 1 gives us a 0, and all the way down the line, we end up with the 8-bit string 00011111. Now, as I mentioned before, that 8-bit string, we're going to split that into 2 strings before we put it into those funny little S boxes, and we're going to take 0001, that's the left half, and 1111, that's the right half. All right, so now we're almost there. So now we got to figure out those S boxes, and I'm going to explain to you exactly how we use them. All right, so our first string, remember, is 0001, and remember those S boxes, you may not remember, but I'm going to remind you, those S boxes each had 2 rows, and they had 8 columns. You may not have seen how many columns, but there's just 2 rows. And so if I can tell you which row and column to look for those 3 bits, right, that we're going to get out of it, that's all you need to know, right? And so how you're going to figure it out is you're going to take that first string, which has 4 bits in it, and we're going to split it up. Right, so that one's going to go, first of all, it's going to go into S1. Secondly, I'm going to take that 0001 and split it into the 0 that's on the very left, and then the 001, which is to the right of that. So I'm just going to take it and just split off the first one. Now that 0 tells us what row we're going to be in. So we're going to be in row 0. And the column tells us we're going to be in column 001. And you may not remember what that first S box looked like, but it was like this. And I should mention, so you see those bold-faced numbers over the columns and those bold-faced numbers before the rows, those are all written in base 2. So for instance, if you go across the columns there, that 000 means column 0, the next one's column 1, then column 2, column 3, column 4, column 5, column 6, and column 7. Those are all written in base 2. Right, so we're looking for row 0, which is the top row, and we're looking for column 001, which is actually the second row, and then there's the number that we're looking for, the 3 bits that we're looking for, that's 010, that is in the 0th row and the 001 column. And so that's the 3 bits that we're going to take from S1. Well, now we're going to do exactly the same thing with the second string and S2. So if we take our second string, 1, 1, 1, 1, that's going in S2. We're going to split that into, now that one is the one on, that first one is the one on the left, and then the 1, 1, 1 is the last 3 digits. And so that tells us we're going to be in row 1, column 1, 1, 1. So row 1 means the second row, column 1, 1, 1 means, well, that's number 7, that's going to be the last column. So here's what our S box looked like. And so if you go to row 1, column 1, 1, 1, that's going to be that one right there in the lower right-hand corner, 1, 0, 0. So that's the 3 digits that we get from our second S box. Well, now we're just going to put those 2 strings together, right? Our first string, remember, was 0, 1, 0. Our second string was 1, 0, 0. And so our output from our expansion and scrambling is 0, 1, 0, 1, 0, 0. That's 6 bits. It's exactly the amount that we need. All right, so now we're almost finished with the encryption. All we really have to do is that, remember that last exclusive OR. Yeah, another exclusive OR. Now remember, we're doing this exclusive OR not with the key, because the key, remember, has 8 bits, but with L0, which has 6 bits. So just reminding you, this is our L0 that we started with, L0 being the left half of our plain text message. Now, these are the 6 digits that we just got from the expansion and scrambling, right? 0, 1, 0, 1, 0, 0. And now we just do an exclusive OR. This is boring for you right now. I mean, you've done this a million times, but we end up with 1, 1, 1, 0, 0, 1. So that's our R1. Now remember, our L1 was way less complicated. We just take our original R0, and that's our L1. And remember, R0 was the right 6 digits of our original plain text message. That is 100101. And then we finally, to get our ciphertext, put those together. So the first thing we're going to do is put R1, and that is, well, you can see it up there. That's 111001. Then we put our L1, which is our 100101. And that's our ciphertext. Now, I do want to remind you, this is a simplified version of what the original DES is. We can all be grateful that I didn't make you do that original one. Actually, I can be grateful that I didn't do the original one, because that one would make me cry. Anyway, so that's our finished encryption of our 12-bit plain text. Now, before we go, I'd let you work on the problem, which, again, I'm never going to make you do more than one round. I do want to explain to you how we would use this simplified version and do it more than one round using the key that we were given. Okay, so again, I should mention, as far as security goes, this is not very secure. For one reason, the part of the ciphertext is actually the right part of the R0, which was the original right 6 digits of our plain text. So not very secure at all. If we really wanted this to be secure, we'd have to do this. We want to do this in several rounds with several different keys. So I'm going to explain to you how we would do that, but I promise you I will never actually make you do this. But you should know how this works. So first of all, we're going to start with our key. In the round that we did, we used a key with 8 bits. But we're going to use a key with 9 bits instead. And this is so that we can actually generate 8-bit keys, some different ones. So what we're going to do first, so we're going to do exactly what we did before, is take the 8 bits from our first 8 bits from our key, and that's going to be the 8 bits that we're going to use in our first round. Now remember, and then our first key is going to be 10110110. So that is an 8-bit key. And then we're going to go through the exact same process that I just described, going from L0 and R0 to L1 and R1. So that's going to be spit out of the end of this process. So that's one round, and if we wanted to stop there, we could get ciphertext R1, L1, and we'd be happy. But what if we wanted to go another round? Well, what we do, first of all, is find another key. And the way we'd find another key is to, instead of starting with the first 8 digits, we'll do the last 8 digits. We'll start with 0, which is our second digit, and then go all the way to the end. And that gives us an 8-bit key, 011011101. And then we'll start with L1 and R1 and go through that exact same process that we went through with our L0 and R0. And then we'll end up with an L2 and an R2. And if we wanted to go again, which we certainly could, instead of starting with the second part of our key, we'd start with the third digit of our key, right? So we start with 1101101, except one thing you might notice about that key is it only has 7 digits. So what we're going to do to get an 8th digit is cycle around to the beginning to that next 1, and then that becomes our third key, 1101101, right? That's third to the end, and then we'll add that 1 that was over on the left, and that is 8 bits, and we'll go through the exact same process to get L3 and R3. Now, we can repeat this process as many times as we like to make it more and more secure, and I'm just going to say if we repeat it 9 rounds to go through all possible keys, then we'd end up with L9 and R9, and then our ciphertext would be R9L9. All right, but again, I'll never make you do more than 1 round. Now, I think now you're ready to work on the SDES activities in the PDF file included with this video.